Ordinary differential equations are really the bread and butter of calculus. They are the one application that is behind the whole development of calculus. Well, what is also true is that the method of separation of variables is probably the bread and butter of differential equations. It is one of the most commonly used methods for solving a differential equation, and so you're going to find it very, very often no matter what branch of engineering you're going to be studying. One of the reasons why it is such a fundamental method is that it is really just a basic generalization of the simplest of all differential equations. What am I talking about? Well, there is a differential equation that, or a form of differential equations that can be written simply as y prime equals some function. Well, the only thing you have to do to solve this differential equation is integrate, right? So you integrate, get an antiderivative, add the c, and you've got your solution for your differential equation. Very simple, provided, of course, we can do the integral. Okay. Now, what we're going to be looking at is a slight variant on that. And the idea is the following. Oh, by the way, as the sentence says there, thank you for reminding me, sentence. The method that we're going to see is really a generalization of what we've done for the exponential model. So it should look fairly familiar to you, but it's a very important, a very widespread generalization. The idea goes as follows. Consider this situation. Let's say that we have a differential equation that looks like this. Y prime equal a function of x times a function of y itself. Remember, a differential equation may have the function itself involved in it. Well, think about it. What are we looking for in the solution of a differential equation? We want to know what y is as a function of x. So that means that y is a function of x, right? So I can write the differential equation as f of x, which is a function of x, times g of y of x, which is also a function of x, right? Okay, so what I can think of is this function is really just a product of two functions of x. Okay, so even though the original differential equation is written as a product of a function of x and a function of y, but I can think of it conceptually as the product of two functions of x. Well, look at where this one leads. What we're going to do in the assumption that we have seen so far is we're going to separate the variables. What do I mean by that? Well, first of all, I'm going to say that an ODE is separable if it can be written in this form. Y prime equal function of x times function of y. Remember, implicitly I can think of the right-hand side entirely as a function of x, but it presents itself as a product of a function of x and one of y. Right? In this case, what I can do is I can use again Leibniz notation, and I can separate and I can write the left hand side as dy by dx, and then I can obtain from that the fact that 1 over g of y dy is going to be equal to f of x dx. Now you can think of this as a playing with the fraction on the left hand side the same way that we've played before, or you can think of it as basically telling us something about the differentials, two differentials. Okay, so we have in fact that both sides are differentials. And they're both differentials of functions of x. Remember, y is a function of x, so I can think of the left-hand side as a differential of a function of x. Only the left-hand side is a differential implicitly. But if both are differentials of functions of x, then the original functions must differ just by a constant as functions of x. So let's see where we can go with this idea now that we have separated the two variables. At this point, what we can do is we can find the originals by integration on both sides. So what we're going to do is we're going to integrate the left-hand side, integrate the right-hand side, and this will give us two functions. On the left-hand side, we're going to end up with a function of y, which again, remember, implicitly is a function of x, and on the right-hand side, we're going to end up with an explicit function of x. So this is already a solution of our differential equation. It does relate y and x, but implicitly. So we're going to call this an implicit solution of the differential equation. Now, if we can solve for y explicitly, meaning the last equation that we have, so if we can solve this equation here in terms of y as a function of x, then we'll have obtained an explicit solution of the ODE. In some situations this can be done, and we're going to be seeing how that is done. In other situations that may not be possible or even desirable or or necessary, and so we're going to simply end up with an implicit solution for the ODE. So this is the general technique. As you can tell, very simple, very easy. Now of course there is lots of details, but those will depend on each case. So I'm going to show you a couple of examples. But then again, you'll have to do, as usual, lots more examples on your own to see what kind of other situations can occur.